Welcome back, students. We're on our second day of probability notes with Mr. Olson, so get ready to have fun.
All right, thank you, Luke. The reason I went back to our example from yesterday, I just want you to remember what, like, I'm recording this right now, Derek.
That's his calculator.
All right, so I want you to remember this problem here because our first example today has to do with this problem. So do you remember this problem from yesterday? This is when we were talking about the students at Pascal High School and the ones that fell into the category of female playing sports and then both. Okay, we good at that? You guys remember that one from yesterday?
Yes.
All right, good. So now let's take a look at our notes from today. So we start with that same exact example right there. I just pulled this from yesterday's stuff. What we found out yesterday is that the probability that a randomly selected student was a girl or they played sports was 0.89. And using the formula, that's how you would find that 0.89. The probability that they're a girl plus the probability that they play sports, but then subtracting that intersection. Okay? The way that we did it with the Venn diagram was we just added the three numbers across in the Venn diagram, right? To me, if you have a Venn diagram, that's the fastest way to do it. But this is how you do it using the formula. Okay, it was necessary to subtract that 0.27 because those had overlapping outcomes. They shared outcomes. There were girls at Pascal High School that also played sports. So when we added those two probabilities together, the 0.54 and the 0.62, you are double counting the girls that play sports because they're counted in both categories. So you have to subtract the 0.27 to get rid of that in one of the two categories, whatever you want to consider it. Okay, so what we call these events then are, well, they're not. They shared outcomes, so they're not disjoint or they're not mutually exclusive. If two events do not share any outcomes, so picture a Venn diagram with two circles that aren't even touching, okay, which we don't really ever draw, right, because it doesn't make much sense. But if there are no shared outcomes, then we call these mutually exclusive events. I don't know if it was in this class yesterday or in the other one that I brought up. If we were to make a Venn diagram on fast pitch players and boys basketball players, there's no shared outcomes there, right? There are no boys basketball players that joined the fast pitch team this year. I don't think there was, right? So that would be, Sam, no? So that would be an example of mutually exclusive events, okay? Because there are no shared outcomes. So we had to subtract that then. So let's take a look at our first example here where we're talking about events that are mutually exclusive. It says, the government designates a single cause of death for each person in the United States when they pass away. The resulting data indicate that 45% of deaths are due to heart and other cardiovascular disease. 22% are due to cancer. Are these mutually exclusive? How do we know that? It says it. It's in, like the first sentence says it, right? Only one cause of death. So there's no way. Now, can a person have cardiovascular disease and have cancer? Yeah, it is possible, right? But the cause of death can only be due to one thing. So these are disjoint. The probability of dying due to either one of those are disjoint. And I just relisted the probabilities there using the probability notation. So let's find some probabilities then. It says, what is the probability that the death of a randomly selected person will be due to cardiovascular disease or cancer? All you need to do is add them together. So the probability of, I can't remember what it was. H is 0.45 plus 0.22. This is 0.67. There's no need to subtract anything because if we said, okay, now we need to subtract the probability of H and C, that's just zero, right? There is no intersection. All right, what is the probability that the death will be due to some other cause? 0.33. Actually, let me write this. 1 minus 0.67 is 0.33. Why? What are these things? What do we call that? Complements. Okay? Dying from either cardiovascular or heart disease is the complement to dying with anything else. All right, I'm going to zoom out here and give you guys a second to jot that stuff down that we have right there. Actually, let me kind of clean this up a little bit. So it says, recall from earlier that the probability of event A and event B happening was found by multiplying the two events together. That could only be done if the two events were independent. Think of the blood problem that we did yesterday, randomly selecting two people, their blood type being this and this. We said, well, these are independent because the people were randomly selected. Once we assumed that it was independent, we were able to multiply things together. If they're not independent, we got to throw another little wrinkle into the mix here. Okay. It says to find the probability of two events occurring if they are not independent, then you must consider, this is this thing right there. Oops, that guy right there. That is the probability of B given A. And I just rewrote it right there, or gave you a spot where you could kind of write it in your own writing. The probability of B given A is the probability of event B if event A has already occurred. It is read as P of B given A, or the probability of B given A. We still multiply this probability with the probability of A if we want to find the probability that A and B occur. So this is how we would do it. We would simply take the probability of A and multiply it to the probability of B, given that A has happened. Because for whatever reason, the fact that A happened affected the probability of B. Okay? And it's a lot. So what I'm going to do before we fill anything else out right there is I'm going to come down here and have you look at this example right here, just to make this seem not so bad. All right? It says if you have a bag of 8 red, 6 blue, and 6 green marbles, what is the probability of pulling 3 green marbles out in a row if you replace the marbles each time and then without replacement? So if we replace the marbles each time, those would be independent events then. Doesn't matter what you pulled out because you're putting the marble back each time. Does that make sense? What is the probability of getting a green? I think there's 20 total marbles, right? So what's the probability of getting a green? Yeah, 30%. I'm just going to say 6 out of 20. I'm just going to leave it as an unsimplified fraction just to show where the numbers come from. There's 6 green marbles and there's 20 total marbles. So the probability of getting 3 greens in a row, these are independent. We just multiply them together. It'd be 6/20 cubed. That is 27 over 1,000 is what it would simplify to, or 0.027. I don't care that you have the 27 over the 1,000. You can just give it right as a decimal. All right, so that's independent. If you're replacing the marble each time, who cares what you got beforehand? It doesn't affect the next probability. Now, this is where things get interesting. Without replacement, these events are not independent. Now, it does depend what happens prior. So then I kind of broke it down like this. The first probability we're interested in is the probability of just getting a green marble on the first pull, which we said is 6/20, right? Probability of getting a green marble is 6/20. Or if you want to call it 0.3, that's fine. But the probability of getting a green marble given that you've already gotten a green marble, and here's why I left these as fractions instead of turning into a decimal. What does that become then? 5/19. There's only 19 marbles left in the bag. You have not replaced any marbles, and there's only 5 greens left in the bag. And then the third probability is the probability of getting a green given that you've gotten 2 greens already. Now that would be 4/18. This should seem very similar to some of the counting problems that we did, right? With the multiplication principle. With and without replacing or repetition of letters or numbers on the license plate sort of thing. All right, so we're just going to multiply those 3 things together. So we're still using the multiplication principle of probability. It's just that we have to account for the fact that the probabilities change because they are not independent of one another. Can actually do a little simplifying here. Let's see. Those are cancel out. Oh, those are gone. So we have 1/57. Whatever that would be as a decimal. Point. It's about 0.0175. Any questions on that? Okay, so here's the deal. That is, I did that because it's one of the most simple examples of conditional probability that you could have. Just drawing without replacement. Okay. Now let's go back and talk about what conditional probabilities are useful for in a statistical sense. All right. So we're back to right about there. It says we can also use this conditional probability to determine if two events are independent of one another. Okay? But in order to do that, we're going to have to know how to find a conditional probability, not like with these marbles down here, but with an actual formula. We're going to put that on the back. But the idea of independence is this. Events A and B are independent only if the probability of B is equal to the probability of B given A. Or if you'd like, you could actually find the probability of A and then compare that to the probability of A given B. Doesn't matter. It's really saying the same thing. This is usually what would be given like a textbook. Okay? Let's zoom in on that a little bit there. So on the back side, we'll give you the formula for conditional probability. The formula for conditional probability is this. The probability of B given A is going to be equal to, in the numerator, we always want to put the probability that both things happen. So the and probability, the probability of A and B. If you want, you can get fancy and use, remember yesterday, that and symbol, that intersection symbol, you can use that too. It means and, same thing. Okay. If you, didn't want that to happen. If you have no interest in taking stats after this, although a lot of you probably have to take a stats course in college, so some of this notation is why, that's why I show you some of this notation. Okay, here's the important thing. This is the easy thing to mess up. Our denominator is always the probability of the given event. So in this case, that's A. The probability of A is going to go down here. Whatever the given event is what goes down here. The given goes in the denominator. That's the important thing to remember. Okay, the numerator is easy. It's always and. It's the probability of both events happening. But the denominator is the probability of the event that has been given. And then I just wrapped up something that we had on the front side, that two events are independent if the probability of B is equal to the probability of B given A. Or you could flip it around. Okay? Got that formula? You don't have to necessarily, guys, you don't have to write all this stuff over here. I just did that so that you could see what I was writing a little bit bigger. You can just put your answers right next to the questions right here, okay? You don't have to rewrite all that stuff over again. But the first thing I want to do is make a Venn diagram. So take a look at example 3, the probabilities they give us. Get rid of this here. It says A and B are events in a sample space S such that the probability of A is 0.7, B is 0.4, and the intersection, the and probability, is 0.2, which is the first one we should put in our Venn diagram. At 0.2, right? So let's do that right away down here. The intersection is 0.2. I'm going to put that this is, so these are generic here. We're just calling this A. We're calling this B. In the middle, we have probability of A and B. All right, let's do that thing that we did yesterday where we just basically fill out this whole Venn diagram, and then we'll worry about what questions are being asked. So what did they say the probability of A overall was? 0.7. So what do I have to put in the just A part? 0.5. There. Now A is 0.7. Only A is 0.5. A and B is 0.2. Together, the probability of A is 0.7. And I think B, if I remember correctly, is 0.4, right? So that means that this has to be 0.2. We good?
Yes.
Okay, so if we added all those across, that would give us the probability of A or B. What is the probability of A or B? 0.9. What does that mean we have to put outside here? 0.1, right? So now we can easily see everything. Just by putting that 0.1 there, we know that if we added those together, we got 0.9, if we didn't already know. Remember that. All right. Let me zoom out here a little bit and put some of these answers up here then. So the probability of only A, what is that? 0.5. The probability of neither, that's that 0.1 that we have. And again, you just put these right next to the problems. The probability of A or B, that was the 0.9 that we got from adding those three values across. Or remember, you could add the 0.7 plus the 0.4 and subtract the intersection. 0.7 plus 0.4 is 1.1. Minus 0.2 gives you the 0.9 as well. That's the addition principle of probability. Okay, now, I'm going to skip over to question F. I added a question there. What's the probability of A or, oops, I didn't really write that correctly, A or B, but not both? A or B, but not both. How would you find that? Say that again. So that would just give you the 0.9 again. If you did the probability of A plus probability of B minus the intersection, you just described that exactly. Right? You could do that, but then you'd have to do what? No. You'd have to, because what you just said gives us this. Probability of A plus probability of B minus intersection gives you the 0.9, right? How can we find the probability of A or B, but not both? Look at the Venn diagram. 0.5 plus 0.2. That's A, that's B, and it doesn't include the both, right? So the answer is 0.7, but I want to go back to what Connor just said, because you could use what he said. You could do this, but then you'd have to again subtract that intersection again, because that intersection is actually counted twice. This subtracts it one time, this subtracts it both times. That gets rid of both of them. All right. I don't know why I have this in two spots. There's the 0.7 on there too. All right. So now to the interesting question. It says, find the probability of, oh, no, I'm sorry. Question E just says, are events A and B independent? Now, really, that's really all the question is. They're kind of giving you a hint by saying, that is, does the probability of A given B equal the probability of A? Now, you can do that, or you can flip it. Do B given A and compare it to B. I'm just going to do what they suggested. Okay, so right here, we're going to find the probability of A given B using that formula from up above. What has to go in the numerator? The and, right? So I'm actually going to write the formula one more time. A and B. What has to go in the denominator? If I'm using this, B. Whatever's given. Okay. I'm using A given B, so I'm going to put probability of B in the denominator. You could switch around and do it the other way. Now, we're going to find this probability in a second. Okay, actually, let's find it, and then I'll talk about, you know, kind of the gray area and whether these are equal or not. So let's actually put these probabilities in. The probability of A and B was 0.2, right? Yes? What's the probability of B? Careful. It's 0.4, right? So this is 1/2, 0.5. So the probability of A, given that B has happened, is 0.5. What was the probability of A without B happening? 0.7, right? Probability A is just 0.7, right? Are those equal? 0.7 and 0.5? Let me ask you this, are they even close in terms of probability? 77% probability and a 50% probability. Not even close. So, and I know I told you not to write a lot of this stuff over here. I would have this written though. We should wrap up this independence question with a nice little statement like this. Since the probability of A does not equal the probability of A given B, and I'll just put like what they were. A was 0.7, and A given B was 0.5. Those are not even close. So what do I mean by that? Well, honestly, guys, when you're doing these problems, you might get probabilities that are pretty darn close, but not exact. Like maybe like 60% and 62%. Well, that might be, depending on what you're talking about, close enough for you to say that they're pretty much equal, right? If you like that kind of gray area stuff and being able to argue your case about stuff, AP Stats is a good class for you. Most of the questions that we get here, it'll be pretty straightforward, okay? 0.7, 0.5, not even close. So what we say is A and B, since they are not equal, are what? They are not independent or independent?
Not.
Okay, let's go back here. They are independent if they are equal, right? They are not independent. And then here's another good little sentence to add on to this. Okay, to show what it means to say they are not independent. Because those were different, there appears to be some association between these two things. Because when B happened, it affected the probability of A happening. So there must be some sort of association here. Okay? It's hard doing this problem with generic stuff, so let me throw this at you. Let's say I surveyed you guys and asked you, do you like apples and do you like bananas? And you could answer that you like both too. 50% of you said you only like apples. 20% of you said you only like bananas. Okay? 20% of you said you like both. All right? And then I realized that the probability of someone liking apples, if I knew they liked bananas, was 50%. But the probability of somebody liking apples overall was 70%. So it seems to me like there's an association between liking apples and bananas. Because if I knew you liked bananas, you didn't like apples as much. That percentage went down 20%. Okay? I don't know if that helps at all. If not, sorry. All right. I definitely want to get into as much of this last one as we can with what time allows here. I'm going to erase this though and erase this. Okay, this is the best example in this entire class. I'm not even lying about that. All right. So I'm glad that we're recording this because I'm really sad that not more people were here for this because this is a good example. All right. So what this says is this. Our school cafeteria serves meatloaf, all right? On any given day, they either serve meatloaf or they don't serve meatloaf. There is a 70% chance that if they serve meatloaf, that they serve peas. If they don't serve meatloaf, there's still a 30% chance that we're getting peas anyways, all right? So we have that going for us. We're either getting meatloaf or we're not getting meatloaf. And if we get meatloaf, we might get peas or we might not get peas. But if we don't get meatloaf, we might not get peas and we might get peas. Okay, there's all this stuff going on. So this is perfect for a tree diagram. The students know, this is my favorite. The students know, and can't you picture the lunch ladies coming up with all these probabilities, right? Like, all right, if we give them meatloaf, there's going to be a 70% chance that we give them peas. But if we don't give them meatloaf, there's still going to be a 30% chance that we give them peas. All right, down here it says, the students know that meatloaf will be served exactly once during the 5-day week. I don't know how you know this. At the beginning of the year, it must have been in like the open house or something. They let everyone know. There is a what percent chance then on Monday that you get meatloaf? 20% chance, right? When you on Sunday night you go to bed knowing there is a 20% chance that I am getting meatloaf tomorrow. 1 out of 5 chance, okay? So actually, that is the first question there. It says, what is the probability that the cafeteria serves meatloaf on that Monday? That is 20%. All right. So let's come down here and start filling out this tree diagram. And the first branches of our tree diagram have to do with our meatloaf consumption. We're either going to get meatloaf on this Monday or we're not going to get meatloaf. Yes?
Why is it 20%?
Because it says it's served exactly once during a 5-day week. Yeah. So this question would be way harder if we started throwing out any day during the week. But we made it a lot easier by saying served once during the week and it's a Sunday night, you're heading into Monday. What's the chance? 20%. All right, so we know that tomorrow there's a 20% chance that we're going to get meatloaf, right? Don't fill out anything else yet. Okay, just put that 0.2 right there, nothing else. I mean, you can have the rest of the tree diagram, but know the numbers. What are the other things that are given to us? I want only the stuff that was given to us in the problem. Okay, the probability that we get peas if we had meatloaf is 0.7, right? So hold on, think about what we just said. The probability that you get peas, given that you had meatloaf, these probabilities are all conditional probabilities. All of those. For example, the one that we just wrote, that is the probability that you get peas given that you got meatloaf. Okay? What's the other? So I just showed you an example there. What's the other thing given to us in the problem? No meatloaf, but still get peas was 30%, right? We good? Let me just erase this. Tamburino, you okay back there?
Yeah.
All right. So I love that because it's on video. So those are the three things that were given in the problem, right? That's it. That's all we're given. Now let's fill out what we know. If on this Monday, there's a 20% chance that we get meatloaf, the probability that we don't get meatloaf is 0.8, right? Those are the only two things that can happen. We can either get meatloaf or not get meatloaf. That's it. Obviously, there's a lot of stuff in that no meatloaf category, but let's keep it real. What about the no peas? What should that decimal be or percent be? 0.3, because now that you've said you have meatloaf, you're either getting peas or not getting peas. In other words, these things are complements. These things are complements. These are complements. If we don't get meatloaf, the probability of us not getting peas is 0.7. Okay, so as soon as I know that I don't have meatloaf that day, I walk in the line and they put a burger on my plate. I'm like, ooh, there's a 70% chance I'm not getting peas today. I know it. All right? And we all think like that, right? Okay. So now, the next thing that we were going to do here is put the and probabilities. These are the probabilities found just by multiplying through the branches of the tree diagram. So the probability that you get peas and you didn't get meatloaf, or you did get meatloaf, I'm sorry, is 0.14. I'm going to put these a little bit closer here. 0.14. So I'm just multiplying through the tree diagram. 0.2 times 0.3 is what? What's 0.8 times 0.3? 0.24. 0.8 times 0.7 is 0.56, right? There's one thing wrong here. It's 0.06. How is an easy, or what is an easy way to know that you made a mistake like that? Guys, these are the only four things that can happen when you go through the lunch line. What do they have to add up to? Those better add up to 1. That's pretty cool if you think about it. All that math that we just did, and those all add up to 1 at the end. Okay? Now that is the meat of this problem, pun intended. Really, you can answer any of these questions now. Let's go up here. What's the probability that the cafeteria serves meatloaf and peas? That's 14%. Make sure you write that up there. Now here's the big one. What's the probability that the cafeteria serves peas? Well, they serve peas here or there, right? So do we add those or multiply them? You add them. 0.14, because you're going to get peas with meatloaf, or you're going to get peas without the meatloaf. So that is 0.38. That is good stuff, folks.